Okay, so we're back with another question here on, just want to make sure that the stream started. Another question here on LeetCode. Hello and welcome. So here we are, and the idea is counting bits. Let's see how we do. Let's give it a shot, see how we do. Given a non-negative integer number num, for every numbers I in the range between 0 less than I and less than or equal to num, calculate the number of ones in their binary representation, return them as an array. Calculate the number of ones in their binary representation and return them as an array. Okay, that's interesting. It's very easy to come up with a solution with runtime O of n times size of integer, but can you do it in linear time? Possibly in a single pass. Space complexity should be linear. Can you do it like a boss? Do it without using any built-in function like built-in pop count in C++ or in any other language. Given a non-negative integer number num, for every numbers I in the range, so all the numbers 0 less than or equal to num, calculate the number of ones in their bit binary representation, return them as an array. Can you do it in linear time, possibly in a single pass? Space complexity should be O of n. No, actually that's not true. Space complexity is not O of n. It's space complexity is linear. Constant. Because int can be put into 32 bits. So linear time, size of the integer. So yeah, let me explain. I don't know if this is what they're looking for, but you can do something like the following. This looks like it's an older problem, by the way. But anyway, so, all right, let's do this. Standard vector, we do an array of integers. We're going to say 32. Say result. Actually, it's good. It's a vector, right? Yeah. Vector int ret of 32, 0. We're going to do the following: for int I equals 0, I is less than 32, plus I. For int j equals 0, really could just start at 1. J is less than or equal to num plus j. And we're going to ret of I plus equals int of num and 1 bit shift to the left I times, and then return ret. Something like this. Output. Oh. Okay. Interesting. What? Not num, it's supposed to be j, I'm sorry. Wait a second, what is going on? Oh, the number of ones in their binary representation. Ah, I see. Oh, I understand. Okay, that's a little bit different. So 0. Oh, okay. I thought it was something entirely different. Okay, understood. So, interesting. You could do O of n log n. O of n in single pass. Space complexity should be O of n. Yeah, well, the thing you're returning is O of n, right? So, okay, I understand. I misunderstood the question. So, yeah, I mean, you're doing it this way then. Actually, it's not really logarithmic. It's still linear. So it's 0, and then just say red dot back. Is that what you want to do? Just plus equals 1? Is that it? Is that all I have to do? Oh. What do we get here if we do this? Output 0, 1, 2. How do we get 2? Wait, what? This should be not 2. What? What is what? So, oh, I see. I think it's supposed to be 31. Still the wrong answer, huh? What? What is going on? I'm so confused. What is happening? Wait, whoa. What? What? Huh? This is so confusing. All right, what's happening here? Something really funky is going on here. So the last number, 1i, j is 2, number of times we see that is 0, right? We don't see that at all. So we should say 0, 0, 0, right? Almost all the way through. And then we see 2, 8, yeah, so 8, 2, and 0, 4, 2, and 0, 2, 2, and 0. Oh, boy. Will, come on, bud. That's why. That's got to be an integer. That's why. That's so confusing. I mean, that's the, okay. Not confusing, but I should have known that. I should have realized that what that was. I feel kind of silly now doing that. Oh man, this should have been a lot faster too. This is a problem that I kind of know the answer to already. Just counting the bits of all the numbers. And I guess, I don't know. What are the limits on this? I don't know. 10,000 will do. Let's do 1 and 0. Let's see what we get for each of these. Alright, let's go for it. Hey, you got there. Okay, faster than a fraction. Okay. Not very fast. Okay. There's another way to do this, which is basically divide by 2 repeatedly. While y... Oh, yeah, there's another way to do it. We would say a little bit more efficient than this. So int x equals 0, and we'll say I is going to be a 1. It's actually if let's do I equals j, right? And we're going to do I and 1, or yeah, I and 1. We can do x plus equals I and 1 int, right? And then we're going to take I, say as long as I is greater than or equal to 0, or greater than 0, then we bit shift I to the right. Okay, something like this should also be correct. Yeah. There we go, it's a little bit faster. So, yeah, that's a slightly less. We could try this again. Do it this way. How about that? Yeah, okay. Yeah, I mean, I don't really know of a more efficient way than that, quite frankly. That's about as good as I can do. So what you do is you set I to be that number, and you say, okay, and it with a 1 that tells you if it's divisible, excuse me, if you end it with a 1, that'll tell you whether or not there's a bit set in the rightmost position. There's actually an even faster way to do this, and I'm thinking about it. So a little bit of bit manipulation. It goes like this. It's you want to find, you take, so it's I equals j, we'll say, okay, so to I minus 1 and I minus 1, what this is going to do is you have I minus 1. When you AND these two together, I want to say it goes something like, how to do this? So basically, I'm trying to figure out a way where this will be 32 iterations anyway. I'm trying to figure out a way where we can do less than that. If you do I and I minus 1, what happens is you would, you actually need the negation if you flip I and do I minus 1. So I minus 1, what that does is it takes everything is the same except if there are a series of zeros from the right to the left, those all get flipped to ones, and the 1 gets flipped to a 0. And then you actually, yeah. And so now you have, if you and I minus 1 with I, you would remove everything. You would actually remove the first bit, really, the first significant bit. And what you can do is you can actually take the negation. You can take the negation of I, flip all the bits, and now all the bits to the left side, all those bits will disappear, and the 0 bit, or that 1 bit, becomes a 0. And when you subtract all these other values, actually no, this will, I don't know if that's not what we want. Hold on, I gotta think about it for a minute. I think if you negate this, flip all the bits, then that 0 becomes a 1. All the other zeros become 1s. I think this basically gives you the most significant bit. And so we'll just say next bit is equal to this. And then what you can do is you set I equal to I minus next bit, or I XOR next bit, right? And yeah, as long as I is non-zero, then I gets set to the next bit, and you increment this guy. So as long as you're non-zero, so basically this is just gonna say plus equals 1, really. So as long as you're non-zero, you're gonna get the bit, the most significant bit, and then you're gonna remove that. So you get this next bit, and then you remove it using XOR, and then you get the next bit again and again and again until you're 0. Something like this. Yeah. Now that's not much better though, which is kind of interesting. Still 8 milliseconds each. It's still relatively slow, which is kind of interesting. So how about, also I don't see how we can use less memory too. Well, I think the less memory is what we're doing here. So I think what we're going to do is you can do I XOR with this. So I XOR with this guy, and then you increment each time, right? Something like that. And that's correct too. However, that doesn't really, we can also do something like this, which is, we can do, I think the num plus 1, 0, and allocate the memory in one shot. And then we can say int, and we could say, yeah, int x equals 0, x plus equals 1, and then ret of j equals x, something like that. That seems to work too. Oh, that's a lot faster. There we go. Yeah, it's much better in terms of memory and speed, right? Because it actually is allocating the memory here, I think, is a big part of the speed boost. So hopefully that's quick. And you know what you can do that's even faster than this is, instead of using a vector, you can use alloc a, right? Alloc A, I want to say. We'll find out if this is run on Windows or... So, oh, we want to improve the efficiency even more than... The reason why this might improve efficiency is... I'm just going to charge the headset a little bit more. I'm actually not sure. I'm thinking about it. I'm not really sure about this. Never mind, I don't want to do that. I was going to say you can use a small trick to allocate this memory right on the stack, and hopefully that would be more efficient, but I'm not sure if that's worth doing. I'm thinking about it. So I want to see. I want to see if there's a way I can optimize this a little bit more. I want to say that there is. We're so close. So close to 100%. I want to say that there's a way to do this a little bit better, which is... what do we do? It's definitely faster. We sped things up a little bit, but you can actually make these operations even faster. I want to say XOR with this. There's got to be a way to just remove that bit outright. Like we don't actually, because this isolates the bit. It's not really necessary to isolate the bit completely. We can do something like this where you don't have to negate. You don't need to necessarily negate this. If you do that, then you get a 0 and a bunch of 1s to the right, and then everything to the left doesn't change. And when you AND that, you get 0s on the right side. And so actually, you don't even need to. I think you can do it this way too. Yeah, let's see what happens if we do that. Oh yeah, that works too. Yeah, it's a little bit better. A little bit better. Can we get 0%? Can we get 100%? Or 0 milliseconds? It's a little bit better on memory. We're so close, man. We're so close. And... can do this. I don't know if that helps very much. Okay, a little bit less memory still, but it's actually a little bit slower. And the reason it's a little bit slower is because of this. The compiler should be able to optimize this though, so somewhat. I don't know, man. The other routine was a little bit more efficient, believe it or not. Man, how do we? How do we get 100%? How do we do that? I want to say we use alloc here to get our array even more efficiently. Instead of going all the way to the heap, we go right to, just put it right on the stack. It would be so efficient. It would be so efficient. It's gotta be a way. It's gotta be a way. We don't need to do this. first one. Save this a little bit. Okay. Oh, look at this. Memory usage. Ever so slightly. We're so close, man. We're so close. Oh, we got 100%. We did it. Hey! Alright, that's probably about as good as we can get. There we go. Sweet. So, that's that solution. Hopefully that makes some sense. That's fun. Alright, thank you all for watching. Talk to you soon. Basically, it's a little bit I mean, simple explanation for this is we pre-allocate our vector. We don't touch the first element because we know it's always going to be 0. We have a counter that we keep track of that we're going to update our array to that counter, and basically we're just going to count how many times we iterate on this loop. What this loop does is it takes a number and sets it to j. It starts off at integers equal to j. As long as we're not 0, then we iterate, and this is going to end up counting. This basically is just going to count the number of bits you have, and the way it achieves that is it takes I and it does a bitwise AND with I minus 1, and what that's going to do is remove the rightmost bit from I, strip the rightmost bit, and yeah, we just count the number of times this iterates. And the way it strips the rightmost bit is you subtract a 1, and if there's zeros on the right side, all of those will get flipped to 1 until the basically they're sort of like carry bits until you get to the rightmost 1, which then flips to a 0. So you have 0 and a whole bunch of 1s on the right, where the 1 is the first 1 on the right side, the first bit on the right side. And I then will have zeros in all those spots and then a 1. So all these values are going to be opposite of each other. And so if you do as a bitwise AND, all of those become zeros. And everything to the left of I stays the same. So you keep all of your other bits. Now something a little more clever would be if you could do the same thing in the other direction. In other words, if you could do the leftmost bit. No, actually it doesn't really matter that much. Never mind. It's so that'll actually remove. So each time you execute this routine, you're going to remove another bit, and that's why you just increment your count by 1 for each time you execute that routine. And I couldn't really think of a better way to do this. There's maybe something better. However, that's what I came up with. So it's a little bit of bit manipulation. It's a little bit more efficient than checking every single bit. Excuse me, because some numbers only have a few bits in them that are set. So, excuse me. There we go. We got the optimal runtime. So all right. So great. So thank you all for watching. Talk to you soon. I'll probably gonna take a couple minutes and then do another problem. So yeah, take care. Talk to you soon. Hope you enjoyed.